I'm going to talk about metamaterials today. And I'm going to talk about it from an electrical engineering perspective. Kind of, I kind of see the world in terms of circuits because they're much easier to understand for me than Maxwell's equations. But I'll tell you where I get my intuition. I'll start by saying a few words about my background and then move on to talk about the research, area that I've obsessed over the 20 plus years, electromagnetic metamaterials. Towards the end, I'll say my thank yous to everyone. So, okay, all right. So my last name often confuses people, right? It's Grbic. It's not missing any vowels, right? The R kind of works as a half vowel. I think they're called syllabic consonants. So, I don't know how this engineering talk is degenerating into a grammar lesson, but, just explaining it. It means coat of arms. So it's the red and white checkerboard emblazoned on the jerseys of the Croatian soccer team. So a little bit about myself. Growing up, I was as close as you can be to a Midwesterner. I guess I was born and raised in Brampton, Ontario, Canada. I received my degrees from the University of Toronto, and got my PhD at the end of 2005. So I kind of listened to my parents. I stayed in school, but I'm not sure they thought I'd never leave, right? I often joke that, it took me about 30 years, actually 31 years to grow up in 3 weeks because I defended my PhD 1 week. I got married to my wife Anne the second week. And the third week, I moved to Ann Arbor. As most of you, kind of drinking out of the fire hose. As you can see, it wasn't a very far move, right? It was 420 kilometers to be exact. I grew up close to the border, but I guess nothing's particularly interesting about that. Most Canadians live close to the border. I heard a comedian a few years ago say, the Americans should be wary of those Canadians. They've amassed along the border and are ready to strike at any time. So, all right. Oh, what did I do there? Okay. As I said, I arrived in Ann Arbor in 2006, but, this was mentioned, Dennis mentioned this, my rad lab or ECE connection runs deeper than that. My academic grandfather, I guess, Gabriel Rebez, was a rad lab faculty member here in ECE. And my PhD advisor was George Eleftheriadis, who did his grad studies here. So George and I like to joke around that it's kind of, it's like an exchange program between the two schools. So as I mentioned, today I'm going to talk about engineered materials or surfaces, right? Referred to as metamaterials or metasurfaces. But before I do that, let's kind of review a little bit about how conventional materials are characterized, right? Material parameters like epsilon and mu, right? Permittivity and permeability. Where are we? Can you see it? Okay. Maybe I should put on the laser pointer. Here we go. Permittivity and permeability, these two fudge factors describe the effects of electric and magnetic, or electric polarization and magnetization. They describe the homogenized or averaged material parameters, right? We can perform this averaging because usually the wavelengths of interest are much larger, right, than the atomic spacing or molecular spacing, right? So in that case, averaging makes sense. If you're talking about visible wavelengths, you're in the hundreds of nanometers, right? Atomic spacings at the angstrom level, so we're talking about 4 orders of magnitude. So averaging then makes sense. So we don't have to consider, if we're going to consider classical electromagnetic effects, we don't have to look at molecular atomic interactions, but actually explain everything through these two fudge factors. Okay, so, different materials, right? And what water has a permittivity, describing its electric response of 77 at gigahertz frequencies. And it drops down to about 1.79 at visible wavelengths. Printed circuit boards that we're very familiar with as electrical engineers have permittivities around 4. And then those, ferrites, like those beads at the end of our cables that prevent spurious radiation, right? They have a magnetic response, and they have permeabilities from 20 to beyond. So we use these two fudge factors to describe materials in general. In the field of metamaterials, we devise our own meta-atoms, our own inclusions, or metamolecules to develop designer materials, like this 3-dimensional structure shown here by my first student, at the University of Michigan. In this way, we can dial in electromagnetic parameters. The main idea behind metamaterials is to go beyond, as Eric said, what you can find in nature, right? In metamaterials, subwavelength inclusions, so little scatters, play the role of atoms or molecules in a conventional material in order to achieve some prescribed electromagnetic behavior. And if the wavelength is long enough, the wave doesn't see the fine features, it just sees the blurred response of the structure. So we construct these materials from small metallic or dielectric inclusions, small electric or magnetic dipoles. We're all familiar with little electric dipoles, right? These little rods where we can experience charge separation and they could act as an electric dipole. Little loops we know from statics, right? We can create little electromagnets. So they can act as magnetic dipoles. By loading these two elements in different ways, we can play with the material parameters. Collections such as these can actually enable a wider range of control over material properties. As we can see here, if we have little sticks, I like to call them, or rods, the scattered field is the electric field is in the direction of the rods, while the magnetic field rotates. But the magnetic field from adjacent elements cancels out, so we're just left with an electric response, right? In loops, the electric fields circle around, and the H fields kind of loop like this, so the electric fields cancel, so we're only left with a magnetic response. So they allow a wide range of control over material parameters. Control over material parameters amounts to control over electromagnetic waves, radiation, guidance, transmission, reflection, scattering in general. Right? So the ultimate goal of this kind of twisted pursuits of loops and rods, right, is total and complete wave domination. We want to arbitrarily control electromagnetic fields scattered from, guided off arbitrary surfaces. This field of metamaterials has opened up new opportunities. It's given us an expanded toolbox to scientists and engineers, an increased design space. We can not only have material parameters that are positive, but we could have material parameters that are negative, right? We can actually structure these materials so that different polarizations of light see different responses. So anisotropic structures, we can make them vary in space, right? Create inhomogeneous materials. More recently, we could add nonlinearities or time variation. So these structures actually change in time. Not only do they vary in space. And actually, the possibility of realizing a material with negative material parameters, as Eric had said, is what kicked off this whole area. So this was kind of the big bang of metamaterials around 2000. David Smith and colleagues at UCSD combined loops and rods to create a medium with negative epsilon and negative mu. Turns out, if those two parameters are negative, the index is negative as well. And this kind of revived an old paper by Victor Veselago from the 1960s from the USSR, which described the electrodynamics of these structures. And what was interesting is he showed that, because it has a negative index, waves actually bend to the same side of the normal, not the opposite side of the normal as we're used to. And even flat slabs of such material can focus waves. So that was kind of very interesting. And I remember at the time as a PhD student reading about this. This is a near field effect, of course, but this was super interesting. That same year, Sir John Pendry, as Eric said, actually said that this flat slab can actually has infinite resolution if it's ideal, right? Of course, there's limits to this, right? Loss and actually granularity, which limits resolution. But it was neat that this lens not only phase corrects, as all lenses do, like my glasses here, right? They phase correct, but they also restore the amplitude of these highly oscillatory waves that carry the subwavelength features of a structure. So these two things actually allow the creation of a superlens. At the time, right, I was a master's student when reading this, developing antennas that are textured at a small scale, subwavelength scale, to promote radiation. I was designing some leaky wave antennas. My advisor and I quickly realized that we were working on metamaterials and didn't even know it, right? We were working on these structures that were actually textured at a very small scale. So these things were textures at a very small scale, so we looked at it from a circuit perspective. And it made sense because circuits model actually structures that are small, right? So we actually applied circuit theory to their design. Also, at the time, I started dating my wife. So that was so a lot of things happened that year. Right? In the Toronto group, we developed this circuit approach to metamaterial design. The concept was very simple. In our undergraduate electromagnetics courses, we always draw this analogy between, transmission line propagation and plane wave propagation in free space, where we say that the shunt capacitance is related to permittivity, of course, it's proportional to permittivity, and the series inductance is proportional to the permeability. So to devise a medium with negative material parameters, what we got to do is we just have to negate the series reactance and the shunt susceptance, and this is the circuit we get with this high-pass network. This network, two-dimensional network, actually exhibits a negative index. So that's all it was, right? That was my PhD thesis. That's simple, right? We just kind of interchanged these elements. We built a lens, this flat lens, using these circuit networks, as I show here, right? So the negative index lens was this high-pass network. The low-pass network on either side was representative of free space. And we showed that we could focus electromagnetic waves to sub-wavelength spot sizes using this lens. So that kind of got me really excited. We submitted this to Science. It got rejected, right? And then we sent it to PRL. They accepted it. But then I was happy to find out weeks later, Science wrote about our experiments. So that was a bit of redemption there. We expanded it in the following years to include anisotropic materials. So if you actually add, elements on the diagonals, you can couple different polarizations. And then you can, greater control over materials, again, is greater control over waves that propagate within the medium. So here's a fun little example. In this example, there's an invisibility cloak that was actually, first thought of by Schurig, Pendry, and Smith. So Pendry, Schurig, and Smith. They described an anisotropic layer here that can actually guide waves around, for example, this cylindrical cavity here in an unperturbed way so that you could hide in plain sight things there. So it's an invisibility cloak. Here's one actually implemented just with circuits. So you can guide these waves right around using just simple circuits. So there's a lot of power in that, right? More recently, we derived multiple input, multiple output structures. So you can actually texture things at a small scale. So you have these little traces here that you can design where you can map multiple inputs to multiple outputs. For example, you can design a very nice beamformer here that has 0 phase problems or aberrations. So you map different inputs to different output beams. You can also operate it in reverse, where you say, well, so you can design a structure where you have some arbitrary wavefront here, some arbitrary field, and what this network of traces does, it decomposes this field into orthogonal polynomials. Right? So in this case, a set of Gram or discrete Chebyshev polynomials. So the signal comes in, and the complex amplitudes of all those polynomials are your outputs. So this is kind of analog signal processing at the speed of light, right? This work has been extended also, this network of metamaterial unit cells, these textured unit cells. Here I show them kind of schematically as little blocks, right? We can design these structures actually where every unit cell is impedance matched to each other. So it's reflectionless. Every unit cell is reflectionless, irrespective of the excitation. So what's interesting about this, right? So the constitutive unit cells possess this unique property of being impedance matched to each other, as well as the surrounding medium, right? So what I can do is now I can, again, map different inputs to different outputs in a reflectionless manner. So I don't rely on reflections or resonances between any of the unit cells. Instead, the metamaterial relies on refractive effects and path length, and therefore promises kind of true time delay behavior or very broadband type of operation. And these types of structures here, designed by Shreithakar and and Jorge Ruiz Garcia, my postdoc. We can implement these structures, these circuit networks, so we can go from structure to medium, effective medium, to circuits, and implement them as these kind of very simple structures of elliptical pins within a waveguide where we kind of control the dimensions of them in order to get this behavior. And here we show that you can create very broadband structures, see kind of lenses and designs that operate from 5 to 20 gigahertz, for example. So, I talked about metamaterials. We've also explored their counterpart called metasurfaces. So this is kind of a weird field, right? Because usually you go from simple to more complicated. Here we went from 3-dimensional structures to 2-dimensional structures to simple surfaces because they are simple to fabricate. So these metasurfaces are finely textured surfaces with intricate patterns that define their electromagnetic properties. As I said before, as the wavelength gets longer, the wave can no longer see the fine features of the surface, but sees this average response. So we can model these structures using effective surface parameters, surface polarizabilities. But as electrical engineers, we like to model things as impedances or admittances. So you can actually model these surfaces and characterize them in that manner. And my colleague Roberto and I first dove into this topic of metasurfaces back in 2007. In fact, metasurfaces back then, these finely textured surfaces that you can design to have tailored electromagnetic parameters, weren't even, in fact, these metals weren't even known by that name at the time. We just thought they were pretty cool. And we thought that so we developed here aperiodic structures. These was kind of, it looks like an array of capacitors, right? But we've taken account of their mutual interaction in a very accurate way in order to create very small spot sizes. So kind of mimicking what that perfect lens I showed you, flat slab, does now with a simple surface. So we could achieve much finer resolution, much finer probing using such structures. And my student, Mohammad Reza Imani, had worked on that and did his PhD. In fact, I think this was the first metasurface, aperiodic metasurface, where integral equations were used to design it. My group also introduced reflectionless metasurfaces, known as Huygens metasurfaces. These are reflectionless structures. Again, you can see, right, the rods and loops, where we design the electric and magnetic responses of these structures and vary them in space in order to control the wavefront. So here we can deflect an electromagnetic wave with very high efficiency with a single array of particles, right? So again, you can see, again, we're tailoring the magnetic response using loops, magnetic dipoles, and the electric response using traces or sticks. We got smarter with time, right? And then we thought, well, we don't need loops and rods. We can actually stack these metasurfaces. And people were stacking metasurfaces, but we can actually, here we showed systematically how to control, if we have, for example, a symmetric unit cell where the pattern, the first and last pattern are the same, and the middle one's different, so you have 2 degrees of freedom. These 2 degrees of freedom allow you to control electric and magnetic response of a structure. If you go to an asymmetric cell, now you have 3 degrees of freedom. These 3 degrees of freedom allow you to control the electric, the magnetic, but also magnetoelectric, which is kind of a weird response where magnetic fields couple to electric dipoles and electric fields couple to magnetic dipoles. So it kind of mixes the fields at the surface itself. So we got smarter with time. We came up with structures that can actually be fabricated through planar, micro, and nano fabrication techniques. We teamed up with others, right, with Jay Guo in a number of these structures to push the frequencies from my comfort region in the microwave and millimeter wave out to infrared. So here we had kind of a cool chiral structure. You know, whatever you hit it with, whatever polarization you hit it with, it rotates it by 90 degrees, irrespective of the incident polarization. Also, polarization selective surfaces. So, for example, a wave that's polarized like this, circularly polarized, gets reflected while a left gets... So these are features that you could achieve with a combination of structures, but now just with patterned surfaces. And that was work we did, as I said, with Jay Guo and his group, and my student Carl Pfeiffer. With Steve Young, research scientist, good colleague of mine and collaborator that's part of the academic family, right? That I work closely with. We we made ceramic structures that can do the same thing. Here, the structures are a bit thicker, but of course, the losses are lower, right? With my student, Andrew Park, gone to also non-reciprocal structures. So surfaces that, that exhibit Faraday rotation. And waveguiding structures, interesting waveguiding structures that kind of mimic the propagation characters you get in magnetized plasmas with my student John Lee. So those are periodic structures. Now, if you vary things in space, you can actually, as I said, you could bend waves in wacky ways. You can convert any field profile to another using mode-converting metasurfaces. Faisal Salami did that. Brian Riker, we can make crisp holograms by stacking two of these surfaces together. We did this at near-infrared wavelengths. And you can go to conformal designs, too. Why stick to planar structures? Here, in these cylindrical structures, you can control waves in weird waves. Here, we created an electromagnetic kind of vortex with my student, Chen-Wen Lin. So those kind of fundamental studies led to a bunch of antennas that we've designed over the years. Ultra-thin planar lens antennas, so these are, usually we're used to an antenna with a lens, right, displaced from it. Here what we do is we kind of spread out the power in an interesting way, but then use this surface up top to correct the polarization, not only the phase, but the polarization. We design near-field antennas where we can actually transmit power efficiently in the Fresnel zone, so at mid-range distances using these kind of diffraction-resisting beams. Also, launching electromagnetic bullets in the near field, so pulses that kind of stay confined and then disperse after a certain region. As I said before, different types of antenna beamformers and analog signal processing structures, but also beam switch systems and even full duplex antennas where you receive and transmit at the same frequency, but now just with an added surface that you place on your conventional antenna. Lately, we've talked more about, okay, I've said we can change things in space, right? And by changing features in space, we can redirect a wave, right? So changing things in space actually allows us to steer a beam or change its spatial spectrum. By changing surface properties in time, we can change the temporal spectrum or frequency too. So here we had a structure that's transparent, but can be modulated in time and it's a transparent window that can up and down convert signals. By changing properties in space and time, right, we can achieve frequency conversion, but also beam redirection at the same time. We've extended some of our time-varying work recently to small antennas, and Eric kind of touched on that, where small antennas, there's some bandwidth efficiency product that you can achieve, right? There's a limit. So maximum bandwidth you can achieve for a given electrical size of antenna. Here, but the assumption is that your antenna is linear in time invariant. So here we're kind of breaking that. We're saying, well, the properties of our antenna now change with time. So all bets are off. And what we're doing there is we chop up our antenna into different modes, different resonances, and we couple them through time variation. So just like a filter that couples spatially different resonators together, here we couple these resonances through time variation. So these resonances don't even have to be close in frequency. And the key is that only one of the modes, one of the resonances actually radiates efficiently. The other ones actually hug to the surface. So using these kind of parametric effects, we can overcome these bandwidth efficiency limitations and increase the bandwidth of small antennas. So I was happy to hear yesterday that this project for MyARPA finally got renewed yesterday. So we were waiting on that. We're in the middle of a crisis. So what I want to leave you with is let's rethink electromagnetic design with this newfound power to transform fields across surfaces, right? Many researchers around the world are working to reduce the size of antennas, right? So directly fed picture frame antennas that reduce the size of our reflector antennas, right? Replace these camera lenses with nanopattern surfaces. improve the connectivity in 6G and beyond by having reflectors that are controllable, right? That give you virtual lines of sight in an environment, indoor environment, for example. So what we're seeing here is kind of, what I'm saying is, let's think about these surfaces and structures in different ways so that, use them for powering objects, for communicating. And I think the key here is, yes, there are antenna technologies that can steer and do all that. But here we're saying a lot of degrees of freedom, having kind of very shitty control, but a lot of different structures, a lot of different points of control in order to increase the control and get the behavior you want. So now, here are my current group members, the folks that are actually doing the work. Here, my PhD students. I'm grateful that they're in the group. My postdocs, Ferris actually was a PhD student also, but now he's a postdoc in the group. And my close collaborators, Steve Young, a research scientist in ECE that I work with very closely. Here's some of the alums, right, that passed through the group, PhD students, as well as Jordan, who is a postdoc. I didn't have postdocs in my group till a few years ago. So these are the people that contributed to the talks, to the work I showed today. But most of all, I also like to thank my family, right? I thank God for my wife, who's been there by my side for half of my life now, right? I thank you, Anna, for all the love and support and for showing that a serial monotasker like me, that efficient multitasking is in fact possible. A successful career as a director of business partnerships, family life. I don't know how you do it. I haven't managed to figure it out myself. And thanks to my twin sons, Michael and Thomas, for inspiring me every day, right? Your love and warmth make me feel like the best dad in the world, even with my many flaws. And by the way, those soccer games in the basement during the winter months actually get me through the season. I also like to thank my parents, Aunt and Maria, for the love, to my dad for the technical skills he passed on to me and his insistence on doing everything himself. I have to admit that, changing the starter in the parking lot of my high school was pretty embarrassing at the time. But I think it was these DIY sessions that inspired me, my brother and my sister, my brother Alex and my sister Vonda, to all become engineers. Thanks to my mom for her patience, creative spirit, and the value she placed on higher education, even though she didn't have the opportunity to pursue it herself. Finally, I'd like to thank this great college, the university, ECE, and colleagues there for being supportive throughout these years, for nominating me for this professorship, and most recently for giving me the opportunity to serve in my current administrative role. I also thank the Rad Lab for being my small home in this large university. I also thank the Tishman family for establishment of this professorship. Thank you all. Thank you for attending. It's great to see you.